So when we look at the calendar, we have the Battery Tuesday from Fluxim today, and also the fourth IBAT annual conference is just a few weeks away. So if you haven't registered yet, please register basically immediately on the website ibat.swiss. And then last but not least, on December 5th, we have Carrosserie Hesse with the electric buses, battery electric, hybrid, battery and overhead lines, buses, and so on. So I think an example how to use battery in an application. So that will be the last Battery Tuesday for this year. I'm looking forward to have the presentation from Fluxim today, which stays under the title Enabling R&D Tools for Battery Research. So when I look at the different topics, there's modeling, there's analysis, and there are in-operando, optical in-operando analysis. So I'm quite excited what that means. And we have two presented today from Fluxim. So I would like to announce Beat Ruhstaller, CEO and founder, and if I read correctly on LinkedIn, chairman of Fluxim since about 17 years. Originally master and PhD graduated at the University of California in Santa Cruz, and later on made the executive MBA at the ZHW, so Zurich University of Applied Sciences, and Sandra Jenach, R&D manager. She made the PhD at EMPA and is working for Fluxim as R&D manager since 2017. So with that outlook, I would like to hand over to Beat and Sandra, and I wish you a very good webinar. So the stage is yours. Let you share the presentation, and as usual, I will start. Recording.
Great, thank you very much for the introduction. And yeah, it's a great pleasure for Sandra and myself to present here in this audience and talk a bit about what we have done in the past and what we are up to in the future in regards to battery research. So I'd like to introduce Fluxim is a spin-off company from Zurich University of Applied Science, where I've headed the Organic Electronics and Photovoltaics group. And yes, we are in Winterthur. We are outside of the university, but not far from the university. We have currently 32 employees, and we also have 7 distribution partners worldwide, which help us reach the customers. The team overview is maybe on this slide, an overview of the very skilled and motivated team we have at Fluxim. It's a really interdisciplinary team of physicists, engineers, mathematicians, and software engineers as well for developing software. Then the main motivation for our work is dealing with emerging display technology, lighting, and also emerging PV technologies. And on the upper row, you see that with displays, we deal with high resolution displays with pixels of RGB emitting colors, and each pixel then has a stack of very thin films of semiconductors on top of each other. And we care about charge transport in these semiconductor devices, of charge transport of electrons and holes, how they recombine to emit light in the OLEDs. Or the opposite device, which is much related physically, is the solar cell or photodetector device, which absorbs a photon and then excites the electrons and holes that are extracted through to the electrodes. So there also for the solar cell, that's the second main market or main activity of our company. There's a lot of research activity worldwide to develop the next generation of solar cells that might follow after the silicon PV. And in these two communities, we have been really focusing on developing and selling enabling R&D tools, which makes life easier for the engineers and scientists in those research groups. Now, I would like to emphasize that the emerging PV solar cell technologies, some of them actually do have a mixed electronic-ionic charge transport. For instance, this perovskite solar cell sketched here indeed not only has free electrons and holes that are moving, but also ionic charges which are slowly moving and can give rise to hysteresis effects. So anions, cations are present in these solar cells, and a lot of research groups are dealing with this. And also very impressive results have been achieved for the solar cells, reaching 33.9%, the latest record of perovskite silicon tandem solar cells. So why am I saying this? Because, okay, also in batteries, we do have electrons and we have ions also in batteries, and we are already used to studying those kind of charge transport phenomena. Now our vision is, as you will see in the next slide, we have a range of products, and with these products, what we want to promote is measurement technology. So the researcher that has an idea and wants to come up with a new material, he then makes a device, and then he can benefit from our measurement instrumentation and do special test structures or full devices, and then maybe vary the temperature and get an experimental curve shown here in blue. And our philosophy is really to also offer simulation software in order to understand what these signatures mean that we measure. And modeling wise, we have several approaches. We can either do equivalent circuit modeling as sketched here, or we can do physical modeling, which is mainly based on partial differential equations that describe the physical phenomena, and we solve these equations numerically. And finally, the modeling also includes the fitting of the model to the experimental data, and fitting then leads us to obtain parameters, material parameters that we can extract. And after a successful comparison of measurement signals and simulated curves, we get more insights and then come up with new ideas and start the development cycle all over again from the left-hand side. So that's our philosophy, to do both measurement instruments and simulation software. With this recipe or strategy in mind, we have already commercialized 6 products. The original product was a simulation tool for thin film devices, OLEDs or solar cells, which is now almost 20 years old. And then we started with measurement instrument in 2012, another simulation tool for large area devices in 2015, and then 3 more instruments over the last few years, and some of them we will see later in the presentation. Now, again, an example of a mixed ionic electronic charge transport device. Perovskite solar cell is an interesting device because it really also depends a bit on the history, how you have treated the device, if you pre-bias or not. And indeed, if you look at the current voltage curve of this solar cell, if you precondition at 1.3 volts, you get a nice solar cell JV curve. But if you precondition at 0 volt, the curve looks much different than the typical solar cell JV curve. And we actually managed to understand a bit better what's going on, and we came up with a simulation of the same behavior. And you see there's a good agreement, and thanks to the simulation software, we can also dive into the device and understand where is the charge piling up inside the device in the case of preconditioning 0 volt or 1 volt. Then we not only look at steady-state JV curves, like here, but we also frequently look at transient curves, like this double pulse experiment, or frequency domain curves, where we look at capacitance versus frequency. And these three types of measurements really give a lot of information about what's going on inside the device, and it allows us to try a global fit of the simulated lines here shown in red, and extracting a set of material parameters by a global fit that matches the measured curves in steady-state transient and frequency domain. Now, talking about frequency domain, let's just remind ourselves a very popular technique that we have been applying in OLED and PV research, but it's also a very popular technique in battery research. So it's impedance spectroscopy, where we apply an offset voltage V0 and an oscillating amplitude with oscillating amplitude superimposed at a certain frequency omega. And then our measurement instrument measures the current and defines an impedance set. So this is the ratio here of voltage and current. And the impedance then can be inverted to get the admittance. And then this quantity can be split into the real part and the imaginary part. And it turns out that especially the imaginary part gives us information about the phase shift that we can have due to some charge transport phenomena inside the device. And the interesting thing about this is we can scan the frequency over a broad range from low to high frequency and understand different carrier transport processes. And as I just introduced, why this is the admittance. And this admittance can be split into conductance and the capacitance with this prefactor of omega. This is how we usually post-process the measured data in the field of PV or OLED. And in the battery research community, we have seen that an alternative way of expressing this impedance is the use of the electric modulus, and then look at for instance, the imaginary part of this quantity M, and then study this resonance phenomena here. But basically, it's just the same methodology, but it's plotted in a different way. And I would like to mention that already a few years back, we had a customer, or let's say a research partner at EMPA Dübendorf, which already purchased our measurement instrument and actually applied it to electrolytes, novel electrolytes for solid-state batteries. And what the colleagues there with Giorgio Di Sastre, a PhD student, what they did with the instrument, they typically combined it with temperature-dependent sample holder to measure the conductivity of the ions in these electrolytes over a broad range of temperatures, because it's interesting to understand also the behavior at very high temperature, and then the conductivity usually is much reduced as you go back to room temperature. So you measure these impedance data, for instance, shown at the bottom left, semicircle and something that doesn't look like a circle, but then the equivalent circuit model allows you to fit that data, the black line here. And another example is this sandwich device where an electrolyte was put in between two electrodes. The impedance measurement is shown here. And for a variation of the temperature, it was possible to determine the activation energy, which is simply defined here in this equation. So the conductivity is split into a density of carriers and the mobility, and also the temperature dependence is there. And there are further methods that allow you to also split or to determine also not only the ionic conductivity, but also the electronic conductivity. And in this particular materials optimization study, there was a mass fraction here was changed, and the ionic conductivity was monitored, and the best case highest conductivity of ions at a position where the electronic conductivity is still limited, that was then the best choice of material composition. So this was the first demonstration of our instrument being applied to battery research. And now I would like to hand over to Sandra. She will introduce you to a research project that is currently running.
Thank you very much. So basically, what Bea just showed, that we have now a background in characterization with our tools, or basically our customer did it, and also simulations. We were now really eager to start the first research project, and there was EMPA who coordinated this activity and invited us to a research project which is running now for 1 year in the in-operando framework. It's called A3SSP. And the project is about, on the next slide, is about thin film and bulk type batteries with either high power densities or high bulk, high energy densities. And our contribution, you can see highlighted there, is on the modeling and simulation part, and also new software and measurement instruments. So I would like to show you here in this first part 2 studies that we just started, 1 year ago, on modeling and simulation of such electrolytes and cathodes. The first one is the transient current method. This was a collaboration with EMPA. Why is this interesting? As Beth also mentioned, you have usually electrical impedance spectroscopy that gives you the ionic conductivity. And this ionic conductivity is a product of mobility and concentration of ionic charge carriers. And it would be interesting, well, from a material point of view, to separate these 2 quantities. But also, as you can see in this sketch here, because the main cost driver for solid state electrolytes is rather the ion density and not the mobility. So you can achieve a high conductivity through enhancing the mobility in the production. So to introduce this method, it's actually pretty simple. So here is a sketch from Moritz Futscher from EMPA. You have basically a solid electrolyte sandwiched between 2 electrodes. You apply a certain DC potential until you reach a steady state, which is shown here. And basically you monitor during this time the current through these 2 electrodes. And if you check then the results, here it's shown for a LiPo film, you basically get from a log-log plot of the current and this transition or transit time, you can get the mobility of the ionic charge carriers. And from the integral, you basically get the ion density. And so this is rather simple and has been done for like multiple variations. Moritz did some thickness variation, and here it's shown that he varied also the bias, because the idea is that if you go to a higher bias voltage, you accumulate more charges, and so there is a limit of high bias, and then you would get the real ionic conductivity density. Yes, so in our simulation, we basically did the same as in the measurement. So we kind of looked at the same curves, but instead of using a measurement technique and using these analytical functions to extract the ion density and the mobility, we used our simulation software that Beat introduced beforehand with certain input parameter to get this synthetic data. And then the nice thing about this is that we can compare input and output and thus do some analytical or validate the analytical model. Yes. And then on the next slide, you can see first results. So here what we show is that also in the simulation, we do an increasing extraction voltage sweep. Basically, the motivation was, again, to move as many ions also in the model as possible. And you can see on the left-hand side, the extracted density from the integral, from this formula above here, if we use the device thickness, and the the comparison with the input, because this is now the beauty of this synthetic data. We now know what we put inside, and you can already see that it's quite far away from each other, so almost 2 orders of magnitude depending on the extraction voltage. And also the mobility, which we would get from the transition point or the transit time. If we use the thickness of the device, we are quite off of the real value. And so the question was a bit, how do we explain that? And now, thanks to the simulation, we can also have a look inside the device. So here you can see the applied voltage, and for 3 different points in time, we plot the charge density profile, or rather just the ion density profile. And you can see here that this is like the full profile, and here is zoom in region on the right-hand side. You can basically see that there is only a little small fraction of these charges that accumulate at the electrodes, and a lot of these charges did not move away from their steady state constant distribution. Or in other words, you can also say that every ion just moved a little bit, but did not cross the full device. So if we now reconsider this in the analysis, it makes us sense that we should not use the device thickness, because the ions do not travel the full device. So what we used instead, or what we tried, is to use something like this debye length, or the accumulation thickness. And here is something we got from a related field, where the electric double layer thickness, how they call it here, can be calculated from the capacitance frequency and plot at different offset voltages. So this was just another simulation where we looked at how does the capacitance scale at different offset voltage. And if we use now this thickness in the analysis, instead of the device thickness, we can actually get a very good agreement with the input value. So here in green, you see the new thickness that we used. And also if we now modify slightly the mobility, analytical formula for the mobility, we can see that if we use the square root of this electric double layer times the device thickness, we get a very good agreement with the input value. So that was very promising. We're very happy, and we wanted to try whether this also works in the experiment. And Moritz now tested it. And well, the first thing we tried was to look at the impedance spectroscopy data plotted in this capacitance frequency. And you can already see that when we change in the simulation the DC voltage, we get a lot of variation in the capacitance over more than 1 order of magnitude, while in the experiment, this low frequency part did not really vary that much. So there was also already a first indication that this probably is not the full truth. And there was also another argument coming from the experimental point of view, namely when Moritz used this formula with the D device, with the thickness of the device, he got a very good agreement between conductivity that he obtained from this transient current method compared to this frequency domain method, so the traditional electrical impedance data. And when he would use the new electric double layer thickness, he would get discrepancy and also a huge concentration, which is even beyond the theoretical limit of lithium metal. So there was a clear argument why this cannot work. And also on the next slide, he even saw that this maximum really approaches also for other electrolytes the theoretical maximum. So the model is only as good as the assumptions were made there. And in the first model approach, we simply assumed that we only have one mobile species, namely the lithium plus ion, or the cation. And as you can see already before, there was a strong accumulation here, but most of the device was basically there was no change in the concentration. And this is because of we have also the static anions which compensate or which fix the anions, cations, and so there was no change, and there was in the end kind of flat potential or even no potential. Now, if we include a secondary mobile species, so the other counterpart, we actually get a strongly different result. So now we get really what was sketched in the first graph by Moritz. We get this accumulation of charge carriers, ions, at both electrodes, and also we get still a field that drops over the full device. So if we do that, we also see that now the analysis works with this device thickness. So now we change the extraction voltage and we really approach with our analysis the theoretical maximum. With the mobility, we are not yet there, but this is really work in progress. So I think we can also move there. And of course, there is need to understand whether this is actually realistic to have also a vacancy that is mobile. And next study that I would like to present is was done by a colleague of mine together with IREC, the Spanish partner in the consortium. And yeah, it's about in situ spectroscopic ellipsometry. To explain a bit the concept, what they do is to measure spectroscopic ellipsometry, so optical probing of electrolyte films or cathodes in situ during charging and discharging of cathodes or model systems in general. And what we did now is to add our simulation software, namely the optical part, and trying to reproduce what they measure to get a material composition, ideally spatially resolved. So as a function of the film thickness, we want to understand what is the composition of the elements in there and how they change. So the approach, or the system first, was this LMO, which is a promising candidate for cobalt-free lithium-ion batteries. And they just put this on top of, I think, platinum electrode. And then they measured, or here on the right-hand side, you can see a sketch or a screenshot of their simulation software. They apply the different charging and discharging currents and changed the time and measured in situ. Here at the top, you can see this spectroscopic ellipsometry function, psi and delta. And here at the bottom, you can just see this one point in energy, or 1 point in energy as a function of time. So when they charge and discharge. This was basically the experimental data set. And now the model works as follows. So first we have to understand what is the composition of the fully charged or fully lithiated and delithiated LMO film. Basically, this was done here. So to obtain these optical parameters N and K for both states. And then one can use this input data and on the next slide, mix these two materials together with a so-called effective medium approximation. So we use a certain fraction x from this delithiated state and 1 minus x of this lithiated state to get an effective medium. And now to parameterize this in x or z direction, we did these small layers, and in these compositions we've kind of fixed the ratio between x, or we fixed the ratio x, and by this you get kind of a profile over the position of this LMO layer. Yes. And here is just an example. So for each time step, one would then need to do a model where you fit psi delta, which is measured with our optical model. And the free parameter is, of course, then this ratio x. And here on the right-hand side, you can then see the profile. So material A and material B, and there would be this linear profile in this case for this specific time step. So to have some first results, this was done at different time steps, as you can see in the inset. And now if the video runs, you can follow how this profile changes over time. Not sure if it works.
maybe you have to gain control again, or...
Try.
The video...
Okay.
Well, I don't see...
Okay.
Doesn't play.
Yeah, sorry for that. But in principle, you can just see that the profile changes over time, the composition, and also slightly the slope changes. So what we want to do next is to allow for nonlinear profiles. Up to now, it was really limited to this linear, not so realistic maybe, profile, and then also look at the sensitivity, like how precise is actually the spatial information that we can obtain from this method. And then, of course, we're ready to try it for different samples, materials, different charging currents, and so on.
Wait.
Okay. Yes, so now you can see over time how this profile changes. And on the left-hand side, you can always see the agreement or the disagreement between measurement and simulation. The measurement is the points and the simulation is the lines. Yes, so this is it. And then I would hand over again to Bernd.
Okay, so yeah, the last statement or comment about this project, we also do work on new measurement equipment. And just to explain, yeah, there's a new software and new measurement hardware to be developed from Fluxim in this consortium. And I'd like to share with you our vision of how to do research in battery cells. Of course, you can do with an instrument like our PIOS instrument, you can do advanced characterization, impedance spectroscopy, pulsed experiments, and get such curves as a function of voltage or time evolution. But then if you want to have statistics, you may want to test many cells in parallel and not only monitor them, but also interrupt those long-term measurements by intermittent advanced characterizations. And for this, we would propose to do multiplexing between multi-channel parallel stressing and then advanced characterization by an instrument like PIOS. And then, moreover, eventually, we also would like to provide physical modeling that goes beyond equivalent circuit modeling. At the moment, our measurement instrument PIOS can already provide customized equivalent circuits to be defined by the user to do the fitting. But in what we understand with what we mean with physical modeling is to actually provide a model based on partial differential equations to also get signals like impedance spectroscopy data to describe the measurements. So this is our long-term perspective. Then software like ZFOS could take care of the electrical modeling. So just to demonstrate what we have done, a similar concept for solar cell testing. So traditional researchers in solar cell research community, of course, you do current voltage measurements with a single solar cell. But then you could maybe be interested in other transit techniques like transit photocurrent, transit photovoltage. But over the years, we have established this all-in-one instrument, PIOS, which can offer many different measurement techniques from steady state to transient to impedance spectroscopy data. Yes, but then traditionally, this instrument only can connect a few cells, like 1 or up to 4 maximum. But if we want to stress many cells in parallel, we have developed an instrument that can measure up to 32 channels. And with a multiplexing approach, we can interrupt the stress testing measurements and do a lot of characterization measurements with the PIOS instrument. More recently, we also, this is particular for solar cells, we offer also a system that can simultaneously measure 56 cells connected to the same instrument. So this is a bit what we have done in the PV field, and we also have the idea to apply a similar approach to battery research. So it's a bit personal taste. Some scientists try to measure lots of experiments with one cell. Others would prefer to just get statistics with many cells and only do a few characterization techniques. But at the end, it's up to the researcher or to the customer what he wants to do. But we try to offer both. So we have started some experimental development of a measurement instrument for multi-channel battery testing, an instrument that should cope with coin and pouch cells. And we are currently working on the electronics of this new measurement system. The idea is that we can run all the channels independently for charge-discharge cycles, and we also want to allow for intermittent characterization techniques like impedance spectroscopy or transient pulsed measurements. And we also offer temperature control in this specific sample holder and instrument. But this is just work in progress. It's not finished yet, but hopefully you will hear back some time in the near future. With this, I would like to summarize our presentation. We have introduced our company and our R&D tool business. We are providing enabling tools to the PV and OLED research community, but we have now started also to address battery researchers. We have shown a few case studies where our instrument has been used, and also our simulation tool has been used for studying thin film solid-state electrolytes. And we're happy to participate in a research project with several partners. This project is coordinated by EMPA, Dübendorf, Maurice Futscher and Jaroslav Romaniuk. And we, in this project, as we have shown, we are testing some analytical models for ionic charge transport. And we also started this optical monitoring method that is based on ellipsometry and optical modeling. And finally, as I just said, the multi-channel battery tester is under development. With this, I would like to thank our colleagues, Balthasar, our product manager for simulation tools at Fluxim. He did this optical in-operando study, provided the models to the data from Spain that came from IREC. And Stefano Sem, he is the one developing our new battery measurement system, and Maurice Futscher closely collaborated with Sandra on those charge transport studies. And here we have the other additional partners in this project: Forschungszentrum Jülich, Extron in Germany, and INNOVA also in Spain. And the funding comes from Bundesamt für Energie. And on the right-hand side, you see our contacts. And I would like to mention that Stefano and Sandra will be attending the IBET annual conference in ABW Baden and are happy to talk to you and get to know you. So we are really interested to collaborate and learn from the battery community, because we're still new in this field, and we would be very happy to understand the needs and also to collaborate. Thank you for your attention.
Thank you very much, Beat and Sandra. I actually open for all the participants the possibility to start microphone and camera, so you can actually get directly in touch with us and ask questions. And otherwise, there's still the possibility over the chat or the Q&A session. I haven't read anything yet in there. Do we have questions from the audience? I don't know actually if that's really working or not. I saw that this function and I allowed it to like everybody. Not sure. I see, for example, that Daniel Chartouni is in the chat. Can we just try quickly if that is working with you, Daniel, or with Andrea Corti, if you can say a few words, or if this is not working? seems not to work. Okay, good. Well, then, well, let's start to ask questions in the chat. I think that's probably the easiest thing. I don't know actually what I have to do to allow you to come in, if I have to do that independent. Well, I think it's pretty interesting what you're doing. The field you see your tools is really mostly in like the development of half cells and cells itself before actually have a final product, or do you see also the possibility to later on do some measurements when you have a, let's say, like production cells? Or
at the moment, yeah, go ahead, Sandra.
The battery testing tool would also be for full cells, but true, at the moment we focus mostly on half cells or just a solid electrolyte sandwich between two electrodes or something like that.
Yeah. Okay.
But then the instrument that's we've shown that can also cope with coin cells and pouch cells, but nothing bigger than that.
Yeah. Okay. Do you see yourself also in a direct competition with traditional electrochemical impedance spectroscopy methods, or you see it as additions, or you see that the traditional EIS methods are not working for like solid state batteries?
I mean, we also in our other markets in OLEDs and solar cells, there are already many other alternative suppliers of other instruments for impedance spectroscopy, but we have managed to offer our own tool, and we try to differentiate by offering more than just impedance spectroscopy, but adding transient pulse techniques or steady state, and then not only offer an instrument but also offer a lot of data post-processing features in the software to add value, not only with the hardware but also with the user-friendly software and customization options. And we hope that we can contribute there, something that is recognized, useful.
Yeah, absolutely. I think the approach of combining it with battery models is certainly interesting. Yeah, and I'm eager to see where that leads. If I understand correctly, you're starting with the modeling, especially the physical based model, as far as I understood it. I guess in 1 or 2 years we maybe know more about where that goes.
Yes.
Do you use for the modeling? You have created your own tools, or you integrate something like COMSOL, or you or?
No, we fully developed our software from scratch with our own source code and numerical methods that usually run locally on the laptop, and you don't need any heavy CPU resources. So we always try to optimize for speed such that you can get a simulation result fast enough to also do some parameter sweeps, or also fitting to extract material parameters. You really need a fast solver. And we learned that with this dedication, ZFUS is mainly a thin film software. So we have mainly one-dimensional transport equations, and which makes it also possible to have fast results, both in charge transport modeling, but also in optics. We have thin film optics and also some light scattering algorithms.
Well, I think that sounds very interesting to me, and I'm happy also to see the progress of this mEranet project. And well, I still don't have further inputs from in the Q&A. Let me check it again. But if not, I think it's time to actually close the meeting for today, and invite you all again to the IBAT annual conference on November 23rd. So thanks a lot to Fluxim, thanks a lot to the audience for participating in the webinar today, and see you hopefully at ABB soon.
Yes. Thank you very much. Thanks for hosting us and inviting us.
Yeah, thank you.
So I stop the recording. Well, good.